All right, let's get started. This is lecture 13, part 1, where we're going to talk about properties of relations. So we'll discuss also Hasse diagrams for partial order and also give some proofs about relation properties. And we're going to discuss what's the definition for total ordering versus strict total ordering. To start, giving a relation, it's a binary relation where R is a subset of A cross A. It's reflexive if the pair AA is part of the relation for any A. So one way to think about in the arrow diagram is if it's reflexive, which I'm using, R to meaning it's reflexive. If I have an element A and I have an arrow to itself. If it's irreflexive, or maybe I or IR, if this self arrow does not exist. Okay, so that's one way to picture it. It's symmetric is that for any pair AB, if AB is in the relation, BA is also in the relation. So let me use S to be reflexive. So if I have relation between A and B, there's a relation between B and A. Of course, anti-symmetric, which I'm going to use AS, or later on you're going to see A, is to say if A and B, and A is, of course, A is not equal to B, and AB is in the relation, B and A is not in the relation. Finally, transitive is that if A and B is in the relation, and B and C is in the relation, then this implies A and C is in a relation. Then the important definition, which we're going to visit again and again, is a relation R is a partial order if it's reflexive, anti-symmetric, and transitive. So if I'm using the abbreviation, if it's reflexive, anti-symmetric, and transitive. I'm using AS or sometimes using A to be anti-symmetric, and IR or sometimes just I for irreflexive. All right. Okay, so keep those definitions in mind. Now we're going to talk about the Hasse diagram. If you have a partial order, the Hasse diagram further simplifies the typical arrow diagram. So it's built from an arrow diagram, but it's simplified much further. First of all, there's no loops. Second is we're using lines instead of arrows because anti-symmetry is implied, and the direction always from nodes that is lower on the page to nodes higher on the page. So if I have a relation A in front of B, I have something like this without arrows. And lastly, you only choose shortest link. For example, if you have a relation which is transitive, remember a partial order, as what we just said, is RAT, or in short, RAT. Okay, it's reflexive, anti-symmetric, and transitive. So it has to be transitive, meaning that if I'm going to use an arrow diagram, I get A from A to B, B to C. Because of transitivity, I have A to C. But for the Hasse diagram, I don't have to sort of indicate there's a relation between AC because it's implied by transitivity. So then what I have is I'm going to draw something like this. A is the lowest one, B is the second lowest one, and C is the highest one, which this implies AB in this Hasse diagram, it implies AB is in a relation, BC is in a relation, and AC is in a relation. Okay. For example, now if you look at a relation, binary relation R on A cross A, there is a pair interrelation if I have less or equal to relation. So if I were going to list element in R, what do I have? Remember, it's less or equal to. So 1 and 1 is part of the relation. 1 and 2 is part of the relation because 1 is smaller or equal to 1. 1 is smaller or equal to 2. Similarly, 1, 3, 1, 4. It also have 2, 2, 2, 3, 2, 4, as well as 3, 4, 3, 3, 3, 4, and then 4, 4. So if I were going to do an arrow diagram, it's quite complicated, but Hasse diagram simplified further to be what I drew here. Because it's, remember the first thing is, it's because it's red, means it's reflexive, means that there is going to be a loop. But then for Hasse in the arrow diagram, but for the Hasse diagram, I'm going to ignore all the loops. Okay. So now, if we look at, first of all, a relation on the power set of X, Y, Z. So what is in the power set? This power set of the set X, Y, Z is starting with empty set, set with 0 element, singleton, set with 1 element, set with 2 element, and set with 3 element. That is the whole power set. Now what I have, of course, you can do a arrow diagram for this relation. But in the Hasse diagram, you will have much less links. For example, in this case, there is a connection between 0 or empty set and then singleton because this is a subset. There's another link between Z and YZ is because the first one is a subset of the second one. Now the question is, how come I don't have this dotted line? It's because this is implied by intransitivity. Because empty set is a subset of Z and Z is a subset of YZ. By transitivity, empty set is a subset of that. But in Hasse diagram, this is implied, so we don't include those implied edges. So now we are going to see some proofs to prove the property of a relation. If I want to prove a relation R is reflexive, then we just need to say, use the definition to prove that A and A is part of this relation. Let's start with a very simple example. Okay. Prove that R is a pair of integer where Y is a multiple of X is reflexive. Remember, to prove something is reflexive, you want to prove A and A is in R for any A that's integer. Let's first look at what are some of the examples of elements. Of course, I can't list all possible elements, but I can list a subset. First of all, 1 and 1 should be this relation because 1 is a multiplier of 1, right? Because 1 is equal to 1 times 1. So it's a copy of 1. Of course, 1 and 2 is part of the element because 2 is 2 copies of 1. Well, 2 and 4 is an element in here because 4 is a multiplier of 2. And 3, 9 is an element in here because 9 is 3 times 3. And of course, minus 1 is element, minus 1, 3 is also part of it because 3 is 3 copies. Oh, sorry. Not minus 1. Oh yeah, should be minus 1 minus 3 because minus 3 is 3 copies of minus 1. Okay. and so on and so forth. This is an influence set. Now we want to show it's reflexive. Remember the definition of something being reflexive. You start with element A that is integer. We want to show AA is part of this relation. How do I show that? Because A is one copy of A, right? It's a multiply. So it's multiply of X is one copy of X. Therefore, A of A. So it's a one-line proof right here. And then this is how you write it. And then the key point of this proof is that A is a multiple of itself. It's one copy of itself. Next thing, if I want to prove something's transitive, the important part is to assume I have two pair. AB is in the relation, BC is in a relation. I want to show that AC is in a relation. That means it's transitive. Again, let's start with example, okay? So this is where you can pause the video and try to solve it within the next 2 minutes. Okay, so if I want to prove something is transitive, I'm going to start with a pair. But first of all, let's look at what some examples in this. It's a pair where taking the second item minus the first item is divisible by 5. So for example, 1 and 6 is in this because 6 minus 1 is divisible by 5. Similarly, 6, 1 is in here because 1 minus 6 is minus 5, which is also divisible by 5. Of course, 2 and 7 is in here. 2 and 12 is in here because 12 minus 2 is divisible by 5 because 12 minus 2 is equal to 10, and so on. This gives you some idea of what type of elements is in this relation. Now we want to show it's transitive. We want to say let A and B to be part of this relation and B and C to be part of this relation. We want to show A and C is part of the relation. Okay, so what is the sketch of the proof? We will let two pair AB in the relation, B and C in the relation. Now we want, because AB is in the relation, by the definition of this relation T, B minus A is divisible by 5. So this is 5 times some integer K. Now, because BC is in the relation, so C minus B is equal to 5M for some integer M. Now I want to show AC is part of the relation. Then what is my ideal scenario? I want to say C minus A is divisible by 5. So this is relying on some algebra. Because we have B minus A is 5K, C minus B is 5K, what I want to do is I want to get at C minus A. Turn out C minus A is actually equal to C minus B plus B minus A, which is equal to 5M plus 5K, which is equal to 5M plus K. Now by the closure property of M plus K, because M and K are both integer, this is integer. So we know that C minus K is equal to 5 times P, where P is integer. So that means C minus A is divisible by 5, which means A and C, the pair AC is part of the relation. Okay, that is a sketch. And here is the proof written down in detail. The key point of this whole proof is a factorization. You use the definition to get 5K and 5M, and then you factor out M plus K. That's it. So to solve this problem, you want to use the hint or the description from the problem itself. You are going to play with divisible by 5. In fact, you use this definition 3 times. All right. Now let's give an example to prove some relation is anti-symmetric. The idea is assuming there is a pair of relation AB is in R and BA is in R, and you're using the definition to show that the only time where both AB and BA is in R is when A is equal to B. In other words, if you think about anti-symmetry, let's go back to anti-symmetric definition. Element is anti-symmetric if for elements that is not equal to each other, if AB is in R implies BA is not in R. In other words, the only time AB and BA are both in R is when A is equal to B. Okay, how do I arrive at that? I can take the contrapositive statement. The contrapositive statement here, if I think about the contrapositive, is B and A is in R implies A and B is not in R, or A is equal to B. Okay. Now let's go back to this problem. All right, it's going to take a while to get there. So we want to prove something is asymmetric. First of all, let's look at what might be elements in this relation, just to give us some idea. I have a pair of positive integer where the second element is a factor of the first element. So for example, maybe 2 and 1, or let's do something more extreme, 6, 3, y is a factor of x, 8, 2, 2 is a factor of A, and so on. To prove it's anti-symmetric, what we are going to show is given AB is in R and BA is in R, show A is equal to B. Okay, so sketch. Start with given AB is in R and BA is in R. But the definition, y is a factor of x. When it's in R, that means A is equal to k times B for some integer k. B is m times A for some integer m. And now we can do substitution. By substitution, B is equal to m times A, which is equal to m times kb, which is equal to b times mk. So now integer b is b times some other integer. Because b is positive, then mk is equal to 1. Because I can divide b by both sides, and I can get mk is equal to 1. And because both mk has to be positive integer, that means m equal to 1, k equal to 1. All right. Then what we have is A is equal to 1 times B, which means A is equal to B. So this shows that my relation R is anti-symmetric. Again, the detailed proof is stated right here. What is the key idea behind this proof? Is you start by giving AB in R, BA in R, and prove that A is equal. The only time this is satisfied is A equal to B. And in between, you are using some integer property and algebraic manipulation to show that KB is equal to 1, which means K is equal to M is equal to 1. Okay. All right, now if you want to prove a relation is symmetric, you want to start with a pair AB in R, and through the property or definition of R, you want to show BA is in R. That is the definition of something being symmetric. So now let's start with example. I have a binary relation on the set A, where the element in there, if A squared minus B squared is a multiple of 3. So again, to give us some intuition, what are some elements in here? For example, 2, 1 and 1, 2 are both elements in here, because 2 squared minus 1 is equal to 3, which is a multiple of 3. Similarly, 1 squared minus 2 squared is equal to minus 3, which is also a multiple of 3. What else? Maybe 5, 4 is an element, and 4, 5 is an element. Because 5 squared minus 4 squared is 3 squared, which is divisible by 3. And similarly, 4 squared minus 5 squared is divisible, is minus 3 squared, which is also divisible by 3. So we want to prove this is symmetric. I kind of play with a few pairs of a few elements in this relation, and they seems to be symmetric, but now we need to prove it. To prove it, we want to show, suppose we have a pair AB that is in the relation, okay? By definition, at some point down the road, I want to show that BA is also in the relation. So I need to basically use the definition of R. Let AB to be part of the relation. By definition of the relation R, A squared minus B squared is multiple of 3, so that is 3k for some integer k. Okay. Now, in order to show BA is part of the relation, I need to play with B squared minus A squared. That is fairly easy because I already know A squared minus B squared. So I multiply minus 1 on both sides. We have B squared minus A squared is equal to minus 3k, which is equal to 3 times minus k. Because k is integer, the minus k is also integer, right? So this is by closure property. So that means B squared minus A squared is a multiple of 3. This means BA, the pair BA, is part of R. So what is the key problem? The key problem here is really you start by A squared minus B squared is equal to 3p. You kind of do a simple algebraic manipulation, and using the closure property, you get what you need. All right. So now let's talk about other types of orders. A relation is partial order if it's anti-symmetric, transitive, and reflexive. So reflexive, transitive, anti-symmetric. An easy place to remember is RAT, if it's a partial order. So why, for example, I want to show this relation is a partial order. You want to show, first of all, it's reflexive. That means 1 and 1, 2 and 2, 3, 3, 4, 4, and 5, 5 are part of the relation, which is true. Now I want to show its anti-symmetry, means that if 1 is smaller or equal to 2, 1, 2 is in the relation, but 2, 1 is not in the relation, okay? So let me just do this slowly. RAT, I need to check each of those properties. Let me use a smaller. If I want to check reflexive, I want to say A and A is part of the relation R. So to differentiate, I'm going to use this to show it's a property I'm after. A and A is in R, so that's reflexive. Anti-symmetry, that means if A is not equal to B and AB is in R, implies that B of A is not in R. So that means, for example, 1 and 2 is in the relation, but 2 and 1 is not in the relation. And finally, transitive, if AB is in there, BC is in the relation, implies A and C is in the relation. So for example, if 1 and 2 is in a relation, 2 and 3 is in a relation, implies 1 and 3 is in a relation. This is true, okay? Now the next definition is strict partial ordering. If it's anti-symmetric, transitive, and irreflexive, okay? Or I or IR. So the difference between these two, one is require reflexive and one is require irreflexive. What does that mean? That means A of A is not part of this relation. So for example, if my relation removes this is the equality, then that means A and A is not part of this relation because, for example, 1 and 1 is not smaller than 1. The next one is total order. If it's partial order, and in addition, if A is not equal to B, either AB is in relation or BA is in relation. The most important part is for or AB. So what does that mean? That means a total ordering is a pair of elements in the relation is always comparable in a way. So it's partial order, that means it has to be rat. And in addition, for every pair, there's a relation. Finally, strict total ordering, if it's anti-symmetric, transitive, and irreflexive, and then finally, it has the same requirement as a total ordering, which means that any two pair of elements is comparable in a way. So now let's look at these properties carefully. I'm going to give you three relations, R1, R2, and R3. You need to define the type. And then those relations are defined on the power set of P. So power set of P, this has 2 to the power 4, which is 16 elements in here. Let's do one at a time. The first relation is I take two set S and T, both are subset of A. Where there's a relation when A is the element in S is smaller or equal to element in B. Okay. We need to decide, is this anti-symmetric? Is this transitive? Is this reflexive? And so on. And is this irreflexive? And is this symmetric? So this is where you can pause and ask yourself this question and try to solve this in 2 minutes. It turns out this relation is a partial order. Remember what is at the key of a partial order? It has to be rat. So that means it is reflexive, it is anti-symmetric, and it's transitive. So we need to somehow show that that is the case. So if it is reflexive, what does that mean? That means for all element that is in S and an element that is in T, there is a A is smaller or equal to element A in S, element B in T, A is smaller or equal to B. When it's reflexive, we know that A is smaller or equal to A, so that we can show the element in R1, whenever, in fact, what you want to do is you start with ST that is in R1, you want to show T of S is also in R1, okay? And similarly, you want to show this is anti-symmetric and then transitive, okay? And then I will encourage you to do this as take home. The next one is we want to say the type of ordering. So what is in R2? Let's list the element in R2. It's a pair of subsets of A, such that the element in the first one is the number of elements in the first set is smaller than the second one. So what is this? An example would be 1, 2, pair with 1, 4, 8. This is an element in R2 because the first set has 2 elements, the second set has 3 elements. So it turns out this is a strict partial order, because what you need to do is to prove that this is anti-symmetric, this is transitive, and is irreflexive. So let's just check the last property, irreflexive. What does this mean? Let's use S. If ST is in R2, implies T of S is not in R2. This is fairly easy because let's start with ST is in R2. What does this mean? This means the size of S is smaller than the size of T. Which means the size of T is bigger than the size of S, right? I'm just switching the order, which means T of S is not part of R2 by definition, because the first element has to have a smaller size than the second element, okay? Again, you can take home to check the first 2 properties for this. The last one is to say the sum of elements, R3, sum of element in the set is smaller equal to sum of element in the second set. What are some examples of elements in here? So, for example, 1, 2 pair with 4 is an element because 1 plus 2 is smaller than 4. 1, 2, 1, 2, 3 is another element because 1 plus 2 is smaller than 1 plus 2 plus 3. So those are some examples of it. So again, let's go back and look at the properties associated with this set. It turns out this is a total order. To check it's a total order, it has to be anti-symmetric, transitive, and reflexive. Okay. Let's check the reflexive property. So that means if we want to show S and S is part of R3, where S is a subset of the powers, element of the power set. Okay. Why S and S? Because if I have S and S, the sum of element in S is smaller equal to sum of elements in S, because I have smaller equal to sign. So this is trivially satisfied. Okay. And again, I would challenge you to try to prove the property of A and T. Okay. So that is for part 1 of this lecture. And have a good night and And feel free to come to office hours if you have additional questions.